Greetings, Earthlings, and welcome to the season 6.1 of Science and Cocktails. Science and Cocktails has the purpose of making you acquainted with all the different forms of scientific inquiry while sipping a famous cocktail and listening to weird, creative, and out-of-space sounds. First teleportation of this season will be guided by the Regius Professor of Chemistry at the School of Chemistry in the University of Glasgow, the one and only Leroy Cronin. He will digress over the recent attempts of answering one of the most fundamental questions in the world. How did life begin? He will tell you how you can slowly begin cooking the primordial soup. First, he will tell you that you will have to add bones from the Kizombo dinosaur, only to be found in Andromeda. Then he will tell you that you will have to check in some Bibalobamba Beta, found in the constellation of Pegasus. Finally, you will need the secret ingredient, spit from a being of planet X31. The final result is the primordial dildo that carries the power of creating new life and should be treated in a sacred way. The words of Leroy Cronin will be transcribed into painting by the artist Harry Schütze, and afterwards the electronic musician Jakob Schmidt and the visual artist Sune Pearson will perform live on stage. End of transmission.
So it's my first evening at Science and Cocktails. I'm speechless, I'm not sure how to follow that intro. However, I will see if we can better the dildos. So in the next 40 minutes, I'm going to tell you about one of the quests we've got in my lab, and it's not a science fiction quest, we're really doing it. And it goes back to a really fundamental question about why we're here, not why are you here tonight, and why did you just see a pink dildo on a TV, but why are we here? And this idea of how we can be a creationist, can we make life in our lab? My research group know I have a God complex, but it's not about my God complex tonight. It's about how can we take something from nothing in terms of making life. I mean, God presumably did make us. And the issue that we have is that as species, as machines, if you view yourself as a machine, you can create things, you can build things. So we are all creationists, yet we are put here by evolution. So maybe the answer to this question about where life came from needs us rather to think about what do we mean by machine. So one of the things, when I try and convince you that this question can be answered in my lifetime, or maybe your lifetime, think about the functional, practical question in the lab. What are we going to try and make? And if you think it's impossible, then look around you. There's quite a few of you here. So I'm going to try and cover all these ideas in terms of how we get from this concept of having or requiring a creator or doing things that are so simple, the need for a creator is actually rejectable. That it is just a series of random events that occur thanks to the laws of physics and chemistry. Before we do that, there is always a problem, and I would go to this problem in a second, but I want to just ask you, what is it doing? And define it. And I'm going to flick some things up. When you think you know what it is, just shout out. What's it doing? What's it doing? Really? Doesn't look like it's flying to me. Yeah, so it's flight. And when we try and think about life and defining life, it becomes really hard because we only have one example of life, and that's our biology using DNA and proteins. There's lots of different types of flight here. Before flight was conceptualized, if we'd had debates for 1,000 years about flights, it would have been a rather productiveless argument. So I'm an advocate for just building the flying machines, even if it's crazy like this. This is my preferred machine. And I think that it would be interesting if we could think about how we can get as many different types of flight. And that's one of the things I want to kind of convince you of tonight. But of course, we should try and define life, and definitions are really tricky. So what is life? There's no one alive in here then. What is life? Shout out. Well, I'm told I'm allowed to swear, and as long as it's not put up on the web against me, life, there's two characteristics that certainly animal life have, and it's fighting and fucking. Okay? So that's one crude way of putting it. But if I give you a complex one, it's a self-sustaining, non-trivial trajectory in a state space. I have no idea what that means. So let's have a more simple one. It's a non-equilibrium entity made by evolution. Okay, can we go a bit, that's still too complicated for me. It's very simple. Stuff that moves with intent. Because if you went to a planet and something was moving around with intent, not randomly, not by, but actually, going and picking up my laser pointer and throwing it at someone, or going and getting another cocktail, then you'd say, oh, that's really interesting. There is something that's moving with intent. And I think this is a very nice functional definition. Those of you that are really interested in definition, this one is correct. I just haven't convinced anyone yet. And I'm not joking. This is actually it. This is what life is. But this is probably as good as we need. Now, what I'm going to try and explain is not only what life is, but can we make a life form? Because we need to have at least some idea of what the experiment is. Because if we spend 1,000 years debating what life is, does it need to have sex? Does it need to move? Does it need to have DNA? Does it need to have these various different things? Then we're going to get stuck. And I'm a very simple experimentalist, and I want to go in the lab, as was elegantly shown in the video, and make my primordial suit and make a dildo that randomly runs around the stage. And actually, that doesn't matter. Joking aside, that's not a bad analogy. Come on, I'm hoping to get another cocktail. So the basic units of evolution are these things. Just look at this for a second. This is a machine that's making a perfect copy of itself from some food. And it's replicating and overtaking. If I went in my lab and I made an inorganic version of this, and I showed you there was no DNA, no proteins, and I showed you the two dishes, and you couldn't tell the difference and these things were growing, would you agree that I'd made a life form? Okay, 3 of you. The rest of you, like my peer reviewers, would basically groan and tell me to piss off. But as a Turing test, an indistinguishability test, it's quite a useful experiment. Can I make a robot that can make a slightly better robot or just make itself with a simple set of boring building blocks. And that's where we're coming from. So that's our thought experiment. What are the important questions? Well, what is life? Is biology special? Is matter evolvable? Matter, at the moment, we design our bridges, we design our costumes, clothes, whatever. We don't tend to evolve things. So if we could start to do evolution outside of biology, as, say, has been happening with, say, evolutionary robotics, or in some design space, that may allow us to have a new technology. Are we alone in the universe? If I can make a life form in my lab, or someone else on Earth can do it, and they can do it simply, I think most of us would be happy to concede, depending on how difficult that life form was to make, because if it was based upon Apple iPhone 10 point blah, 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 then probably not. But we would say, okay, there is life elsewhere. So wouldn't it be wonderful if we can make simple life on Earth and show that that probably could occur on other worlds? That's quite an important question, I think. Can we make open platforms for synthetic life? Could everyone make their own life form, like their own pet? Why not? That would be cool. Well, we do make life forms. They're children. And what new technologies will come from a kind of inorganic life? So these are some of the questions out there, and maybe people have questions about, is the Terminator going to take over the world? Is everything going to be destroyed and, biology become irrelevant? Or is what we're doing just simply impossible? What specific questions do we have? Well, I'm really interested in discovering if there is a new physics or a new series of rules that separates the creation of life from the evolution of life. I don't think, if I ask everyone here, is anyone here, I should say a Republican, I'm not saying, does anyone here not believe in evolution? Cool. So I think that we know that, so I think I can leave that lesson, and evolution actually works. So we know that evolution, I think we'd all accept that evolution is capable of taking bacteria and turning them into you and me and really complex, interesting stuff. The jump comes from sand to cell. There must be new physics there, I would argue, or new chemistry, I'll call it, to annoy the physicists. There must be some new physical phenomena that we don't understand. And it may be different to what a living system is, and that's one of the things we're hoping to do. Is it a tendency or property of matter? And can we engineer or discover non-biological systems capable of evolution? The origin of life question is very old. People have been asking this for millennia. But we have spent more money on the origin of the universe, Hubble, and the origin of mass, CERN, than we have the origin of life. So I'm going to be passing a hat around, and I'll even take... I know you don't have the krona, but you only have krona, but that's fine. But it's really important that this is a big question. We've been asking it ever since we've been thinking who we are, what are we doing here, where do we come from? Yet we really haven't tackled this. And it's because we've thought that it was an impossible question. And I want to convince you, hopefully I'm not boring you yet, or won't bore you, because the chemistry lesson is coming. Oh yeah. Really lots of chemistry. Oh, cocktail. Sorry, I need to get this. This is very important. Thank you very much. Oh my God, it's alive. Can you still hear me? I'll put the microphone in it. Anyway. Now, come on, you're not supposed to look like a comedian. So, here comes the chemistry lesson. Now, I want to ask another question that I asked my research group. So, I am a professor in chemistry in Glasgow, and I'm very fortunate to have a lot of very talented people who come from all different walks of life, roboticists, mathematicians, biologists, and chemists. And we work with lots of international groups, and one of my collaborators is hiding in the audience with a research group tonight. I'm not sure if you want me to point him out, though. It depends how the talk goes. If it goes badly, I'll keep him anonymous. But there's really interesting things to do with molecules. So can molecules think? Okay, are you made of molecules? Are you thinking? Now, I think we'd agree that the ethanol in there, not always, yeah, but the ethanol in there is not thinking. But the ethanol I'm drinking it's going to distort my thinking later. But molecules in a system think. So what is it about molecules in a system that allows you to think? And what is it about molecules in networks that give rise to life? Now, this is just chicken wire carbon. It's just to show you that this molecule can be made into this molecule, this molecule, this molecule. Now, if I can make this molecule, and it can make this molecule, this molecule, this molecule, this molecule, and then I can feed one in down here, maybe I can make a kind of juggling act where I can continually add in simple stuff and make complicated stuff in the middle. Maybe that's what life is. But the problem is, if we try and engineer it, we will fail. And for the last 50 years, we've tried to engineer it. And for the last 50 years, we've tried to take it apart. And this is why we have not got much further on the origin of life. What else is life? Well, life tends to, you're quite hot, right? When you're dead, you're cold. So one other definition of life, and it's not entirely proven and robust, but living things tend to be defined by their ability to die. Okay? And that's a pretty good test. You know, is it alive? Is it alive? Can I kill it? Shit, it was alive. Because it's no... And so that's quite important. I'm feeding you, you're feeding you, the planet is feeding you, you are then burning, and you're using that available materials and energy to dissipate, and dissipate constructively sometimes. So how do molecules and random things go from randomness to something as complex as a cell? Now, this movie here I didn't do myself. I actually stole it, and I'll give the credits to whoever wants it if they want to get it. And this movie here shows, it's a very caricatured version of what's going on in a cell in terms of tubulin being made, disconstructed, molecular machines moving things around, proteins being made. And you can see there's a lot of things happening in the cell. Here, this is suddenly the ribosome, which is taking DNA and making proteins. You can see out it squirts. It's like spaghetti being chucked out. And so all these things are occurring all the time, all these molecular machines. All these molecular machines have a given chance of formation. But I don't know if any of you bet. The chances of this naturally occurring from zero is impossible. And so this is where the creationism has to come in, or does it? Is life impossible because the cell is so complicated? How much time do we have? 4.5 billion years of planet Earth, 4 billion years of cells, 3 billion years of photosynthesis, 2 billion years of complex cells, 1 billion years of multicellular life, and how many million years of human beings? I don't know. I'm hoping at least 500 million more, but you never know. We may make the transition to the robot life quicker than we think, if you want it, that is. So there's a time scale here. So one of the biggest problems that people think against us in making life is time. Why? Where's the problem with probability? Let's take an alphabet. Let's take this, no chance of this text string spontaneously arising. So if I was a monkey in my room with 1,000 monkeys typing away, how long would it take for me to write this text string? And who would care? Well, it would take, basically the probability of this arising is about 1 in 10 to the 60. I think you'd agree that that is 0. Okay, and it's not going to occur. And even then, who is going to be around to read that to say, okay, you've actually written Shakespeare or whatever? And this is the argument that people have been using in a so-called world, which you may have heard called the RNA world. That one day, the planet was sandy, fire, suddenly, randomly, a book starts writing itself. There's no one there to read it, it just writes itself and just says, screw you, screw you, screw you, whatever it's going to say in Danish. And this is what the RNA world people think happens. I hope there's no one really live streaming this, because otherwise my career is over. So this is what people call the RNA world. But I'd rather be a creationist. At least I'm admitting it. It's like, yeah, God made it. Rather than they're saying, oh, randomly on a Tuesday, the book wrote itself. I mean, that is even worse. It's almost disingenuous. And so what I'm saying is the reason why I'm excited and I'm doing experiments is the origin of life, or the ability to make life, has to be simple. Because we exist. It has to be easy. We are not a fantastic miracle. Well, I am. As I tell my mother, or my mother, shit, got it the wrong way around. So now I'm going to talk about molecular miracles. This video here shows one of the things I love to do in my lab, and this is to make a molecule out of molybdenum oxide. And you can see this template molecule in here and all these bits going around, these Lego bricks. In Denmark, I can use it. And this molecule builds itself. Now, this molecule here has no chance of forming randomly. The probability of this molecule forming is 1 in 10 to the 120. But it forms in a millisecond in my beaker. How does it happen? Is God in my beaker? Am I really a creationist? Well, I am, of course, God to my students, but this molecule I didn't make. And the trick was before. This molecule, the reason why it's so hard to make is it's got 154 atoms in it. And that means you'd have to take 154 atoms and shake them in your bucket of Lego, and they would form this perfectly. And you don't have enough shakes available for the lifetime of the universe for it to happen. However, if I replay the movie again, you'll see something. And you'll see this really small molecule. It looks pretty sexy and complicated, but actually, it only has 36 atoms in it. And the probability of getting 36 atoms to go in my shakes is easy. I can do it in a test tube of water. And so what this experiment showed us is that a high probability molecule gives us a low probability molecule. It's a bit like a cosmic fluke. So this shows us that we might start to be able to take simple chemistry, it takes a leap, and can make more complex molecules for free. You don't need to worry about the chemistry or the mechanism, that's boring. Just take it from me, I can make really big molecules, and they're really cool. And it's a molecular wheel as well. So the idea that perhaps life might have come from a warm pool with lots of these simple building blocks that randomly assemble is not a bad idea. I'll tell you a quick story I haven't told. I bought myself a lawnmower. There's not any lawnmower, it's a robot lawnmower with a battery. And all I do is I set the perimeter of my garden with a wire, and this lawnmower goes out. And the algorithm, I was like, oh, it must have a video camera, it's videoing where it's going, I've been there, I've cut that. Screw that, it's random. It basically says, what's your area? 1,000 square meters. Yeah, I'm gonna go randomly that way, 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 and it covers my grass. And it looks like I have a real gardener that I paid to look where he or she was going. And it was random. And so one of the things that we have to get rid of is this idea that random is rubbish. Random events can help us, and that's where the interesting chemistry may come. But the other problem with the origin, as I said, is you've got this chemical soup 4 billion years ago, the RNA world, which I said is impossible, then you get proteins and DNA, you get the last ancestor. This is where we understand this bit is entirely inevitable, and some of us even so highly evolved we wear a tie. So, this is obviously the pinnacle of evolution over here. But we don't understand this bit. This bit. How do we get from here to here? And this is what we're going to focus on. And as I've said, we think the emergence of life was fast. 500 million years? This experiment has to be done in 5 years, right? I'm going to get bored. I don't have 500 million years. But the timescale from complex chemistry is fast. So what we're trying to tell people in the lab is that we have got this chemistry Apollo, we're going to go at the moon. Well, we're not going to quite go at the moon, we're just going to make really complicated shit in a pot and wait until life comes out. So that is exactly the chemistry Apollo. So how to create life? We need to understand how to engineer evolution. And this is the phase transition. Basically, we've got sand make this transition to things that can evolve in time. This is the only graph I'm going to show you, but I thought I had to show you a graph. I pretend at least to be a professor. But basically, we want this to happen. I'm going to do random reactions in the lab, and at some point, I'm going to make a mess. And actually, okay, sorry guys, I would not use the dildo, but it serves my time. I was a dildo, right? I wasn't You put in random stuff, and you shake it. And if you keep doing that in chemistry, you get more and more of a mess. But what we're hoping to see is that literally the equivalent of a dildo putting out. A non-random object emerges. Okay? Not a dildo, okay? I wish I hadn't spotted it. And so there is a kind of event that occurs where we have this life form. So the question is, do we need a big lab? Is it a question of scale? Let's assume that life took 400 million years. We've got the volume of the sea is, of course, 1.3 times 10 to the 24th centimeter cubed. Write that down. No, write it down. And the number of water molecules is obviously 4.58 times 10 to the 45. Just remember that. That's the easy one. But in all seriousness, if you can think about the number of seconds in 400 million years, the number of water molecules, and the number of times they collide, you can give yourself 10 to the 54 dice rolls. Have I got life? Have I got life? Have I got life? Have I got life? I'm still bored. Got life? Got life? And so at some point, you have some probability of getting something simple. And what we've got to try and do is make the simplest machine that can then go on to make a more complicated machine. We can't go for the iPhone immediately. There's actually a real thing about this. I mean, I hate selling Apple products. We can do whatever later. You can buy these cheaply from me. And this is serious, right? Joking aside, think about this for a second. If I was to destroy every semiconductor factory on Earth that makes silicon chips, even though I had the knowledge, how long would it take me to build the machine that could build the machine that could build the machine that could give me this? This did not, Bill Gates or, Steve Jobs did not go in his garage and make a chip. He got it made in China, okay? And who then made it based upon other well-controlled semiconductor rules. So the phone didn't just spontaneously emerge. And we'll come to that in a minute. Let's go back. I do have delusions of grandeur and world domination, but I'm not allowed a world. I'm not even allowed a beach or a pond, but I am allowed a flask, okay? And so what we're trying to do in the lab scale is work at this and make it smaller to the test tube, to microfluidics, to droplets, because as you can see now, there's only one of those, few of those, thousands of those, millions of those, trillions of those, quadrillions of droplets. So if I actually break the reaction up into smaller and smaller objects, I can throw more dice at once. So I can cover more time just by having more space. This is what I tell my colleagues in the building when we're trying to get a new building. And the idea, of course, one day is to get to the point where we are able to create a machine that can make itself chemically and looks like a bacteria, but doesn't have to be. So we're going back to evolution. Obviously, this is what we think evolution looks like if you're not a creationist. This is what I was trying to say here. So you may know this is Babbage's counting machine. This is some kind of typewriter. This is, come on, it's the X Spectrum. I don't know what that is, Apple crap, PC crap, iPad crap. I really like this. But now I can play Jet Set Willy on VMware. So it's awesome. Anyway, but the point I'm making earlier is how simply can I make this iPhone again? There's a nuclear war. It's destroyed all of factories. How long does it take? And this is what you need to think about when you're making a life form. The RNA world would say, nah, you just randomly shove some sand in a pot, in a cement mixer, and out will come an iPhone. Okay, that clearly doesn't work. But it is possible to make one. And so this is the inspiration we're using in the lab to try and make it simpler and then work out how we can stand on the complexity and make it more complicated. It's a bit like having children. I've got 2 boys. Their life is far more complicated than my life. They need far more phones and objects and text messages and all this shit. When I was their age, I just, got put to bed at 4 o'clock or whatever it was. They get more complicated. And so it's just time makes things more complicated. We also need replication. And replication, we're making molecules that can recognize each other like this. You see, I just made that bond there. So this would happen randomly. But now, because it's already made, other building blocks, you can see that this now helps make itself. So it's a bit like one hand making the other, and it would carry on and make lots of itself. So this is the thing we're looking for in our molecular soup. The other thing we need, a bit like DNA, is not just readout, but the ability for mutation. And that's quite important. So replication with errors. It's a bit like doing your tax return and being told you've got more money or less money. It's a bit like what happens in the UK normally, but anyway. And we're trying to do this in my lab with inorganic molecules. And the reason why we're doing them with inorganic molecules is we have access to lots of different building blocks occurring. And these are just representations of our nano Lego that we can add and make all these real molecules. These are real molecules we can make in my lab. And they look a bit like a combinatorial problem. You would take some of these, chuck them together, and you randomly like this, 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 and this. And we described how that works. So you can get a lot of inorganic structures, sand, if you like, that look like proteins for free. So that's one of the starting points. But let's get serious, because I only have about 3 or 4 hours left. And the creation of the life in the lab, so how are we going to do it? It's a pretty serious endeavor. And it all started with actually hacking chemistry. And I'll show you what I mean. Do you know what we're building here? Yeah, 3D printers, rip wraps. Because I don't know what you do. I tell you what you can do with a 3D printer is you can print sex toys, right? You can print the dildo. It's probably about the only good thing you can do with them. But actually, I did this workshop a few years ago, and the idea was to make a 3D printer. And the nice thing about a 3D printer is it has a microcontroller, it has a stage, you can move around. Suddenly, you've got a robot slave. And you've got a robot slave that can do chemistry for you. And so what we did is we used the 3D printer to do chemistry, and we were able to use turn the 3D printer into a test tube that could make itself and add chemicals and make new molecules. And yeah, we published this paper in this journal, and everyone thinks I can now 3D print drugs, and my name is Heisenberg, and if you really want that talk as well, I can do it later. No, I'm not going to. But the reason we started using 3D printers is we needed to start maximizing the number of dice rolls. I think hopefully I can convince you, we need to do as many experiments as we can in parallel and look for something interesting, take the interesting things and throw away the boring things and do more interesting things with them until we can get something that looks like a life form out. And yes, we're cheating because we're searching using a robot, but it doesn't matter because we can audit our cheating. And if we audit our cheating and record how we cheat, we know what the probability of that naturally occurring will be. I don't care how we're going to make life, right, inorganic life. I just want to do it any way I can and then work out how badly we cheated. It's not like with synthetic biology where we're just completely copying what exists, taking some DNA, bunging it in another cell, reconstituting everything. That's really not, that is cheating. Like, that's really cheating. That's so cheating, it's not even tell you anything. But we'll talk about that seriously later. So the idea is to unify large-scale reactions and 3D printed fluidics to kind of create a chemical internet. And that's what we've been doing in the lab, and trying to take the test tubes and put them into this. We've got arrays of reactions that we can do. And they need to be plug and play. And the idea is a bit like making a machine as massive as the Large Hadron Collider in terms of colliding space. But really, I'm a molecular fascist, and I'm going to tell you why. This is my evolutionary engine, and I'm a droplet fascist. Again, I hope this is not being recorded for wide dissemination. And I'm going to show you why. So I've got some imaginary inputs here. Well, I take some chemicals, and I make them into droplets here, salad dressing. And then we put the salad dressing into an arena, and then we kill some of them motherfuckers. I always tell my kids not to swear for cheap laughs, but I'm quite nervous, so it's good. But you can see here, this selector decides whether it lives or dies. And so this is a schematic, so you could do this at home, right? You could make some droplets and then select them, or can make cakes, whatever you want. Feed them to your kid. If your kid dies, you know not to make that cake again. If the kid is happy, you carry on making the cake. Bad analogy, but you know what I mean. And you can recirculate them. So you've got death and life. So now you've got them, and they're boring, right? They're just boring droplets. But suddenly you can start to then put in, using an algorithm, you can start to search for interesting chemistry. And so what we want to try and do is make some engines where we take bucket chemistry, like here, like in the Miller-Urey experiment, we've got this see the spark? So we're just cooking up everything, and we insert it into droplets, and we start to program the chemistry. And it looks a bit like this. Well, this is how you don't want your kids to look like at school. Look carefully. Friends, 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 gang up. Very unhappy child. Now, okay, these are clearly droplets that are just evaporating in a dish. But it kind of looked lifelike, didn't it? Just for a few seconds, just say yeah, go on. Thank you. Well, wait till the end. And so the idea was, could we try and use a 3D printer or a robot to basically create that type of environment whereby we could actually do chemistry in a printed matrix and then search that matrix for lifelike entities. It's a bit like building a chemical engine that we can actually physically slot together. Well, with the help of colleagues, this is something we've done in the droplet space, and I'll show you the droplet robot here. So this is called, we call it Dropbop, and this here is basically a robot that puts droplets in a dish and looks at the droplets with this very funky white piece of paper and does image analysis. And all this does is it takes 4 of the most boring chemicals you could ever think of, mix them at random, and put them in a dish. How boring could that be? But then when you think, oh, well, that space is, there are, not only are the chemicals boring, but there's 17 million different recipes you could do. If each experiment takes about 6 minutes, and you give it to a PhD student, you know how long it takes them? Come on, someone's good at maths. No, 500. 3 years I could get away with and say, get in the lab and stop moaning, I'm not building you a robot. 500 years and the student says, piss off, and you say, we'll build a robot. And that's what we did. But the nice thing is, if you tell a student to do random experiments, they're going to get really depressed and cry. Because they want to think they're doing something interesting. And my students are real superstars, by the way, but it's just to make a point. The point is you start randomly. So what we did here is we started off and we did a lot of random experiments, and we got all these different behaviors. Motion, diffusion. Remember, it's the same chemistry. Exactly the same chemistry. They divide, you get wall division, and the only thing that's different is the recipe. They even explode. They just give up. And so they wobble, so maybe what we'll be doing later when the music goes on in a trance. And so you randomly get these emerge, so the robot is able to see these behaviors. And what we were able to do in the next steps is actually take these behaviors and evolve them in the robot to make the diffusion better, to make the vibration better. Yeah, this is like... So these are the 9 random behaviors we found in the boring salad dressing that everyone said was boring, would never do anything. And this is why the chemistry experiment is interesting, because you get novelty in them. Yeah, we'll stop there. So now what we did, looking at droplets, is we took those inorganic molecules that form really large, complex molecules that you can't see, and we were able to get them to make machines themselves. So we took these we call them nano-molecular libraries, molecules, and we let them copy each other, molecular replication, And then we make these inorganic cells. And these are made out of metal oxide. No cheating, there's no lipid in there, there's no organic. This is made out of tungsten oxide. And we can actually inject stuff into it and make a real Frankenstein cell. And so what we were able to do is combine the nanoscale and the droplet scale. And then we're able to start using the environment to play around with it. And the color change in here is actually a metabolism. So there is what we call a redox reaction. It's basically a battery. So we just injected a battery into the cell. I know it's cheating, but isn't it cool? We injected a battery into the cell. Well, it's not even a battery, it's a bit of rust, but it acts like a battery. And so what we've been able to show, at least at some level, and this is not yet published, but we've almost finished it, is that we have a replication process where this molecule makes this molecule, and this molecule makes this molecule. Look, I've done a video, it's got to be true. And they all go around and get really, really, whoa, there's lots of molecules everywhere, but they form the membrane, and the membranes then start to replicate when you feed them, but then they speciate, okay? And then they start to obviously take over the entire world, and we're all doomed. So what actually happens in the lab when you make droplets like this? So I'm going to keep talking about the prospects for this, and you just have to look at what happens with a droplet. If something interesting happens, just tell me to stop. So what we've tried to do is now put in the library of chemicals into the droplet and allow it to start doing some random reactions and select. And we select for droplets that can split into two. Look at that. That's probably the most profound video I've seen in my entire life, apart from, I don't know, a Britney Spears video or something. But these things can reproducibly divide. And this one has a different chemistry going on. You see the spikes coming out of them. It's the way the focal length is changing against the lights. So the cells themselves are actually vibrating. So they are spending some energy. They then become killjoys at this moment because they were supposed to be separated, but obviously they couldn't bear to be apart, and they join up again. And so we use it so that they're having sex, right? But I hope to convince you here that we discovered this process using a robot that did random chemistry. And what we did is we said we did random, and like, well, okay, we're bored of random. We said, okay, we are now selecting from all the droplets where one droplet that makes two. And then we are exploring the chemistry that goes on in here. And you can see that the chemistry that's going on in here isn't just passive, boring. There is some kind of energy process going on. There's a metabolism built in there. It's very primitive. And so what we're trying to do in the next steps is to add this together at lots of different levels. The take-home message from all of this is that random chemistry in a bucket is probably how life began. And the way we do it is random chemistry needs to become less random. And there are a lot of really good theories around how that can work. And it's a bit like the fact that the laws of physics work and the periodic table is there and you can basically have rocks and so on. Not everything is random, but there are chance happenings. So the chemistry can combine. And this is where we are in the lab at the moment that I can show you. There is actually, if you are interested, genuinely interested, there is a paper coming out in Nature tomorrow. I spent some of the time talking to people today, trying not to give too much away, but we've actually put things called amino acids in these droplets. And what we've been able to do is join the amino acids together to make very primitive proteins. The proteins are the things that DNA via RNA make. They're the proteins, they are the machines that do the stuff in the cell. And we've been able to show that randomly we can make proteins that have structure. Because all chemistry isn't the same. It's a bit like human beings. They should all get on. When you have a team, they should all be happy. Some people just don't talk to each other. Some people spend all the time talking to each other. Amino acids are the same thing. And what we've been able to show is that by heating up and cooling down these amino acids, we can make proteins, or very small fragments of proteins, that have functions with no DNA. And this paper comes out tomorrow. I wasn't sure. They only told me yesterday it was coming out tomorrow, the cheeky gits. Otherwise, I'd put more information in here and gone, look at how awesome we are. But I think this is a really nice image to finish on. I'm now at 41 minutes, and I'm going to stop talking to you and allow you to ask questions or buy me cocktails or just generally ridicule me and finish here. Thank you very much. It's a pleasure to be here. Thanks to the crew for putting this on. It's been amazing.